Today's lecture is going to deal with non-real numbers for some of it. So that's why it's called complex eigenvalues. Let me show you the following. I want to diagonalize this matrix. We have 1, 1, -1, and 0. Now, the first thing we usually do is compute the eigenvalues. So for that, we set this determinant equal to 0. And so we have 1 minus lambda, -1, 1, negative lambda equals 0. And then we'll have, when I do the determinant of this, remember to go main diagonal first, 1 minus lambda times negative lambda, and then minus this direction, so that'll be plus 1. Now let me multiply this all out. I'll get a lambda squared minus lambda plus 1. And to solve this, I'll use the quadratic formula. And if you remember, we get negative b plus and minus b squared, that was -1 squared, minus 4 times a times c all over 2 times a. And that looks like 2.1, doesn't it, instead of 2 times 1. Let me make that times a little bit more in the middle. All right, then we get 1 plus and minus. Inside of the square root, I get -3. And usually when you see this written, this is it's perhaps easier to write it like this. Put the I in front. That's just the way most people do it. I guess the I, when you put it in behind it, it looks like it might be part of the square root or something like that. But anyways, we have two non-real complex eigenvalues. All right, so right away, we're already in a situation we haven't had before. We've always had real solutions to these problems. Now they're complex. Now what do we do after this? Determine or find the eigenvectors. And so we'll start, I think I'll start with lambda equal 1/2 plus I times radical 3 over 2. I'll put a dot there just so I remember that it's multiplication, although I don't think I'll forget. Then we take the original matrix, which was 1, let me see what it was again, 1, -1, 1, 0, so we had 1, and then we're going to subtract off the eigenvalue. And then we're going to have a -1 in that spot, and then we're going to have a 1, and then we're going to do 0 minus that same eigenvalue. Well, let me fix it up a little bit as much as I can and simplify a little bit. So for this part here, I'm going to get 1 minus 1/2 will give me 1/2, but then I'll have minus I times radical 3 over 2. I have a 1 here, I have a -1 here, and then I have -1/2 minus I radical 3 over 2. And don't forget it's augmented with zeros. Now to simplify this, it looks pretty bad, but realistically what I can do is I can multiply, since this is just a 1, I can multiply by the negative of this number times this and then add it, and it will zero it out. So what I'll do is I will multiply row 1 by -1/2 plus I radical 3 over 2. That's an R2, and then I'm going to add it to R1. Well, of course, the second line is not affected by this. But the rest of it is. When I multiply 1 by this number, I get this number here. And so when I add it there, I get a 0, which is exactly what I wanted. This is going to be a little more complicated. And I want to show the work so that to remind you how multiplication with imaginary numbers works. So I have to take this and multiply it to this and then add it to this -1. So let's see what happens. I'll have -1/2 plus I radical 3 over 2 times -1/2 minus I radical 3 over 2. The way you do this is with the FOIL method. So I'll start with -1/2 times -1/2, and I'll get 1/4. And then I'll do -1/2 times -I radical 3 over 2. That will give me a positive I radical 3 over 4. Then this part, which I believe is the inner, I'm going to get a negative I radical 3 over 4. And then this right here, the last, I'm going to get I radical 3 over 2 times negative I radical 3 over 2. Remember, we know that I squared equals 1. So when I do I times -I, I get negative I squared, which is -1. I made a mistake. Negative I squared, of course, is positive 1. So what will happen when I do that last piece, I'll get positive 1. For the I will disappear. But radical 3 over 2 times radical 3 over 2 is equal to 3/4. So when I simplify this all out, the 1/4 plus the 3/4 will be 1. And then this part here with the i's, they actually disappear. So when I multiplied to this piece, I got 1. And then when you add to -1, you get a 0. So they're a little more complicated, of course. So what we have here is x plus -1/2 minus I radical 3 over 2 times y. That's equal to 0. Let me solve for x. Now, your eigenvector is not going to look pleasant here. I'm going to create it in this fashion. I'm going to allow y to equal 1. Remember, you're allowed to let, since you're dealing with a span of vectors, you can let y be absolutely anything except 0. Then x is this stuff up here. I should probably have given myself more room for this. My x then is 1/2 plus I radical 3 over 2. And there is my eigenvector. Now, one thing that's good about dealing with complex numbers, the original matrix had real numbers. And you may or may not remember this, but when I solved here, all of the coefficients on this polynomial were real numbers. So with that happening, you'll notice that I got two answers. Let me put it this way, I got 1/2 plus I radical 3 over 2, and the other one was 1/2 minus I radical 3 over 2. Well, this second piece is called the conjugate, and you're guaranteed to get that conjugate each time. So this here is one vector. Now the beauty is, I told you about the conjugates. Another eigenvalue, the other eigenvalue, that's 1/2 minus I radical 3 over 2. it yields the following eigenvector. So notice you kind of like have conjugate vectors. Let me show you a notation here. If lambda equals 1/2 plus I times radical 3 over 2, then if I put a bar over the lambda, that means its conjugate. That equals 1/2 minus I radical 3 over 2. Well, if I can use the same notation for the vector, there's v. I'll put a bar over it to indicate the conjugate of v. So v and its conjugate v with a flat bar over it are the eigenvectors. So that's nice. Once you get one eigenvector, you get the second one automatically just by finding the conjugate. So my diagonalization looks like this. So I'm going to have 1, -1, 1, 0. That was A. And then remember to make your matrix, you're going to put your eigenvectors, 1/2 plus I radical 3 over 2, 1. And then 1/2 minus I radical 3 over 2, 1. And then we have the diagonal matrix where we put the eigenvalues. So I'm going to put the first eigenvalue that goes with the first eigenvector, I plus radical 3, 1/2 plus I radical 3 over 2. Zeros in the off diagonals. And then 1/2 minus I radical 3 over 2. And then the inverse of that thing, of the first matrix. 1/2 plus I radical 3 over 2, 1. 1/2 minus I radical 3 over 2, 1. Inverse. Now, what I want to do is I want to check this, not because I think that I need to check it, but what I want to do is check it to make sure that it multiplies out correctly, but at the same time give you a review of multiplying and a bunch of other stuff with complex numbers. So let me go ahead and start this. This is not going to be an enjoyable process, I guarantee you that. But let's start. I'm going to take this row and match it with this column. So all I have to do is 1 plus I radical 3 over 2 times 1/2 plus I radical 3 over 2. I think I'm going to give myself a lot of space here. So I'm going to have 1/2 plus I radical 3 over 2 times 1/2 plus I radical 3 over 2. Of course, then the 0, that didn't do much here. Then for this p, when I do this row with this column here, all I'm going to have is the 1/2 minus I radical 3 over 2 times itself. Let me give this thing a name here. This is P. This was equal to, what did we call that? D for diagonal. And then this was P inverse. Because I'm running out of room on this side over here, I'm just going to put my P inverse. I'll handle that in a little bit. Next, when I do this row times this column, that's very simple. I get 1/2 plus I radical 3 over 2. And then when I do this row with this column, I get 1/2 minus I radical 3 over 2. Let me multiply these all out. So FOIL, as usual, I'm going to get 1/4, and then I'm going to get 1/2 times I radical 3 over 2. So that will be I radical 3 over 4. And then it's going to happen again. And then, so that was this inner piece. And then the last, I'm going to get I squared times radical 3 over 2 squared. So the I squared will be negative. So I'll change this plus to a minus sign. And then I'll have radical 3 over 2 times itself is 3/4. Now let me do the same thing with this. Probably the only thing that's going to be different is the middle terms are going to be negative, and you're still going to get this last term. So everything's going to be the same. 1/4 minus I radical 3 over 4 minus I radical 3 over 4. But the same thing's going to happen over here. I'll still get a negative 3/4 because negative I times negative I is positive I squared, which is -1. And then down here, I'm going to get, this will stay the same. 1/2 plus I radical 3 over 2. And down here, 1/2 minus I radical 3 over 2. Let me finish this off and put my P inverse after it. Now let me simplify a lot of this stuff, and then I'll be able to put the P inverse in a little better. So let's see what we have then. 1/4 minus 3/4 is -2/4. So -1/2. And then I radical 3 over 4 plus I radical 3 over 4 is 2I radical 3 over 4. So that's I radical 3 over 2. And over here, the same thing is going to happen almost. I'll get -1/2. So let me continue what I was doing. -1/2. But then I'll have minus I radical 3 over 2. And then down here, these stay the same. And now I'm ready to do P inverse. So let me put down what P was. That was 1 plus I radical 3 over 1/2. Let's see what else was up there. 1/2 minus I radical 3 over 2. And then I had 1s down here. Now for a 2 by 2, if you'll recall, to find its inverse, there is sort of a formula for it. Okay, the first thing you do is do the determinant. So if I do the determinant, I do this part. Let me put a big old dot. 1 over, so you know that I'm finding the determinant of this thing. I'm going to have 1 plus I radical 3 over 1/2 plus I radical 3 over 2. Remember, you subtract, or you divide by the determinant when you're doing the inverse. And then this way, I'm going to have minus 1 times that. So I have minus 1/2 minus I radical 3 over 2. Let me make this a little bigger so it can contain all of that. Will I have enough room? Good question. I'll move the page over so I do. And what you do in here is you swap the diagonal entries. So my 1 is going to go up here. And in the bottom right corner, I'll have 1/2 plus I radical 3 over 2. And then you make the off diagonals negative. So I'll have -1/2 plus I radical 3 over 2. And then -1 here. And now let me simplify a little bit. Whatever this number turns out to be, I'm just going to throw it in the front. I see that the 1/2 cancels, so that's gone. I radical 3 over 2 plus I radical 3 over 2 is just I radical 3. So I'll have 1 over I times radical 3. Now, let me do the multiplying. When I take this row times this column, I'm going to get negative, well, let me write it out. I'll get negative 1/2 plus I radical 3 over 2 minus 1 times negative 1/2 minus I radical 3 over 2. That takes care of this. Then this row with this column is going to be fairly brutal. So I have to do this times this plus this times this. All right, so let's throw that all in. Negative 1/2 plus I radical 3 over 2 times negative 1/2 plus I radical 3 over 2 plus, and then we have negative 1/2 minus I radical 3 over 2 times, how much over, oh look, I can go over more, good. 1/2 plus I radical 3 over 2. All of that is the second entry. Now, for this next row, I'm going to have a similar situation here. I'll have this times 1 minus this. So I'll get 1/2 plus I radical 3 over 2 minus 1/2 minus I radical 3 over 2. And then finally this row to this column is once again going to be a brutal thing. I'll have 1/2 plus I radical 3 over 2 times negative 1/2 plus I radical 3 over 2 plus, give myself room, then I'm going to have this number times this number. 1/2 minus I radical 3 over 2 times 1/2 plus I radical 3 over 2. And then let me go ahead and end that. So I need to do some serious simplifying here. Remember, the original matrix had real numbers, so let's see. I'm really interested to see what happens here. All right, let's take a look at what we have here. Negative 1/2 plus 1/2 goes away. I radical 3 over 2 plus I radical 3 over 2 is I radical 3. Now for this next piece, I'm going to FOIL everything out here. I'm going to get 1/4 minus I radical 3 over 4 minus I radical 3 over 4. And then the lasts here, I'm going to, I times I is negative 1. So I'll get a negative 3/4. Now I have to do this one as well. So I'll start here, minus 1/4. And then I will go here. That's minus I radical 3 over 4. Then in here, I'm going to get minus I radical 3 over 4. And then finally, this last one here, negative I times I will be a positive 1. So I'll just get plus 3/4 here. Okay, now I'm working in this piece. Let me end it off. Hopefully that's enough. I'll erase that if it's not. This 1/2 and this negative 1/2 go away, and I end up with a similar situation before. I radical 3 over 2 plus I radical 3 over 2 is I radical 3. And then down here, FOILing again, 1/2 times negative 1/2 is negative 1/4. And then I have to do 1/2 times I radical 3 over 2, so I'll get plus I radical 3 over 4. Then these inner ones, I'll get minus I radical 3 over 4. And then finally the last, I times I will be negative, so I'll get negative 3/4. And then same deal over here. 1/2 times 1/2 is positive 1/4. And then if I can sneak it in here, 1/2 times I radical 3/2 is positive I radical 3/4. The inner is negative I radical 3/4. And then finally, to finish it off here, I got a negative I squared again, so it's positive 3/4. Well, let's hopefully, I can see these first two were supposed to be 1s. That was what A was when it started. It was 1, negative 1, 1, 0. So I hope this comes out to negative I radical 3, and this comes out to 0. So let's see what happens then. All right, let's simplify all of this stuff up here. The 1/4 cancels with the negative 1/4. This negative 3/4 cancels the positive 3/4. Now I have a bunch of I radical 3's. As a matter of fact, I have 1/4, 2, 3, 4. 4 I radical 3's over 4, and they're all negative. Negative I radical 3. So let me get rid of those. Oh, I just used them all up. I have an I radical 3 here as well. And then down here, this is where I hope ends up to be 0. Those cancel. Those cancel. I radical 3. Oh, look good. Those cancel. And those cancel. And we have 0. And now, when I multiply through by 1/I radical 3, I get 1, negative 1, 1, 0. And remember, that was the original matrix. So I was able to diagonalize it, but we had to go to complex numbers. So here's some notes I want to say. If we have to remain in the real numbers, then A equals 1, negative 1, 1, 0 cannot be diagonalized. Because it's eigenvectors are complex. So once I broke into complex, I was unable to do anything. You can see the eigenvectors. So the eigenvectors were what? We had 1/2 plus I radical 3/2, 1, and its conjugate, 1/2 minus I radical 3/2, 1. So remember, this was the vector, and this one here is what we called its conjugate. So these vectors here, the span of these vectors, they are linearly independent, by the way. You can clearly see that this second vector is not a multiple of the first vector. You cannot find any number to multiply to this to give me its conjugate. So this span, though, happens to equal all of the complex numbers squared. So the complex numbers look like this. C squared, all those numbers in C squared look like this. You have an A plus BI, and then you have a C plus DI. Those are the types of vectors in C squared. So while this spans C squared, if you go back to all the stuff that we did, when we were doing those proofs, we didn't really use the fact that real numbers were used at all. Basically, they could take R, swap it for C, and you're still going to be good to go. What happened to us? The culprit is the characteristic polynomial. In this case, P of lambda was equal to, let me see if I can find out what it was. I think it was lambda squared minus lambda plus 1. This polynomial is an irreducible quadratic over the real numbers. So if I have to do real numbers, I cannot factor this thing. However, in the complex numbers, we have this. And so you can see that the polynomial completely, what they call, splits. That means you can break it up into linear factors like this. And you can clearly see what the zeros of this polynomial are once you break it up like this. If you have to use real numbers, you can't break up all your quadratics. The best you can do with any polynomial, so let me see this, any polynomial, with real coefficients, factors into linear and quadratic factors. I'll do a very quick example of this. I'm not going to show you, well, I think in some sense I may show you a little bit. But consider this polynomial, f of x equals x cubed minus 1. Well, I happen to know that that breaks down into x minus 1 times x squared plus x plus 1. So this piece right here is a linear factor. This piece here is an irreducible quadratic. If I were to try to break it down, I would go into complex numbers, and well, as long as we're stuck with real numbers, we can't go any further than what I have here. So here's the gist. If we only wish to use real numbers, then we can only do the following. We can still break it up into something like we had before, PCP inverse, except now P will consist of the vectors REV, I'll explain these in a minute, IMV, and C equals A negative B, A, B. All of these numbers will be explained in just a minute. All right, so what we're relying on here is that lambda equals A minus BI is one eigenvalue. And what else do we have? We had V, the eigenvector that corresponded to that one was 1/2 minus I radical 3 over 2, comma, or 1. what I'm going to do is break this up into two pieces. 1/2, 1, and then plus negative radical 3/2, 0 times I. So what we have then, the way this is described, is the part not attached to I. This here is called the real part. And this piece here, not the I itself, but just this piece, is the imaginary part. So when I write REV, I'm talking about the real part. And then when I'm talking about IMV, I'm talking about the imaginary part. Not the I attached to it. So both of these are real. All these numbers are real. So real part and imaginary part are talking about real numbers. Similarly, I don't need to do it, but the real part of lambda is A, and the imaginary part of lambda is negative B. So we carried over to vectors as well. Well, here's what we have then. P, the P that I'm promising that you can have is 1/2, 1, negative radical 3/2, 0. And the C that I'm promising that you can have is, let's take a look. My eigenvalue was 1 minus radical 3/2. So I probably should have put that was, this is for the eigenvalue 1/2 minus I radical 3/2. So the A, when I look at A minus B times I, the B is radical 3/2. So the A is 1/2. So I'll have a 1/2. Then I'll have negative radical 3/2. Then I'll have a positive radical 3/2. And then A again, I'll have 1/2. So accordingly, here's my breakdown. A, which was the matrix 1, negative 1, 1, 0, will equal P, C, P inverse. And let me go ahead and put it, and I'm going to multiply it out just to show you that it actually does work. 1/2, 1, negative radical 3/2, 0. See, 1/2, negative radical 3/2, radical 3/2, 1/2, and then P inverse. So for that, first thing, where did P go? There it is. I have to take the determinant. The determinant is positive radical 3/2. So 1 over that is 2 divided by radical 3. So I just turned it upside down. And then let me go ahead and place the appropriate numbers here. When you're doing the P inverse, you swap the diagonal elements. So I'll have a 0 there and a 1/2 there. And then you negate the off diagonal elements. So I have a negative 1, positive radical 3/2. Now, what I'm going to do is, to make my life easier, I'm going to factor a 1/2 from this matrix, a 1/2 from this matrix, and a 1/2 from this matrix. So with that in mind, if I take a 1/2 from the first matrix, I'll be left with 1, negative radical 3, 2, 0. Then if I take a 1/2 from the second matrix, I'll get 1, negative radical 3, radical 3, 1. And then if I do it from the third matrix, I'll get 0, radical 3, negative 2, and 1. So let's multiply it all out. Meantime, I'll cancel a little bit here. I'm left with 1 over 4 radical 3. So I'll start with the first two matrices and then I'll attach that one at the end. Here I'm going to, when I do this row to this column, I'm going to get 1 times 1 minus radical 3 times radical 3. So that'll be 1 minus 3. I'll get negative 2 in that spot. Now in the next row, I'll get this row with this column. I'll get negative radical 3 minus radical 3, so I get negative 2 radical 3. Now this row and this column gives me a 2, and then this row and this column gives me negative 2 radical 3. And then I still have to attach 0, negative 2, radical 3, 1. All right, now I'll have negative 2 times 0, they disappear. Negative 2 radical 3 times negative 2 is 4 radical 3. That's a good thing because I knew I had a 1 in that spot. Next, I'm going to have negative 2 radical 3 minus 2 radical 3, so I get negative 4 radical 3, which is good. I had a negative 1 in that spot. And then 2 times 0 doesn't do anything, but negative 2 radical 3 times negative 2 radical 3 is 4 radical 3. And this last one, hoping it'll be 0. 2 times radical 3, 2 radical 3 minus 2 radical 3 is in fact 0, because this will turn out to be 1, 1, negative 1, 0, which was A. Now, I sort of mentioned if P of x is a polynomial with real coefficients, then it can have non-real zeros, as we've seen. What happens if a plus bi is a 0, then so is its conjugate. And that'll be a minus bi. So you may see something like this. You may have P of x, let's say that equals an x to the n plus an minus 1 x to the n minus 1 plus dot 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 plus a1x plus a sub 0, and each of the coefficients is a real number. Then when you go to factor it, so factor, you'll have something like this. You can always pull the an in front when you factor things out, and you'll end up with something like this: x minus, I don't know, x1, x minus x2, dot, dot, dot. And somewhere down the line, you'll probably have this. And so it's a combination possibly of linear and maybe quadratic factors. Why do I say quadratic? Because look what happens here. If these are imaginary numbers, but look what happens when I multiply this out. I'm going to use the FOIL method to multiply this piece out. So when I have this, x times x will be x squared. Then I'm going to have minus x times a minus bi. And then I'm going to have minus x times a plus bi. And then I'm finally going to have plus a plus bi times a minus bi. So notice at the very end I have the number and its conjugate. When you multiply a number times its conjugate, you always end up with a real number. It's a very simple formula, actually. Let me keep my x squared. Now when I do this part here, I'm going to get negative xa, and then I'll get negative xa again. So I get negative 2ax is there. But then I get a positive xbi and a negative xbi, so they cancel out. Let me FOIL this piece out here. I'll get a squared. And then look what happens when I do the next FOIL. I'll get negative abi, but then in the inner, I'll get positive abi, and they go away. For the last, I'll get negative bi squared. Well, remember, that's the same as plus b squared. So what I'm saying is when you factor it all out, everything could have real numbers. And once you put this in its quadratic form, it has real number coefficients as well. That's why we can only break these down sometimes only into quadratic and linear factors. No matter what, though, the theory of polynomials with real coefficients tell you that you can never have a factor more than a quadratic. That is, in theory, you can always break every polynomial with real coefficients up into linear and quadratic factors. There's no such thing as a cubic factor or a quartic factor or anything like that. All of those can be broken down into smaller pieces. So, anyways, here's what we're going to be dealing with. For the rest of this section, like I said, or video section, whatever, we will concentrate on a factorization A equals PCP inverse, like that which I showed you above. Here, all the entries in every matrix, all the entries are real numbers. So, while we can't diagonalize, many times we can get it into a form that's similar to diagonalization, and it has some interesting mathematical properties as well, which we'll talk about also.